1900, an Italian physicist named Alessandro Volta stacked alternating disks of zinc and copper separated by cardboard soaked in salt water. Electricity flowed. He had invented the first true battery, the voltaic pile. And the most remarkable thing about it is that you can build an identical device right now with materials from your kitchen for about $3. 225 years later, the chemistry has not changed. The physics has not improved. The only thing that has changed is that a $50 billion battery industry has been built on convincing you that the $3 version does not work. A saltwater battery, also called a saline electrolyte cell, operates on the same electrochemical principle as every battery ever made. You need two different metals and an electrolyte solution between them. The metals have different electrochemical potentials, meaning they have different tendencies to release or absorb electrons. When connected by a conductor, electrons flow from the more reactive metal to the less reactive metal through the external circuit. That flow of electrons is electricity. The electrolyte provides a path for ions to move between the metals inside the cell, completing the circuit. Zinc and copper are the most accessible metals for a homemade battery. Zinc has an electrochemical potential of negative 0.76 volts. Copper has a potential of positive 0.34 volts. The voltage difference between them is 1.10 volts per cell. That is nearly identical to a commercial AA alkaline battery, which produces 1.5 volts. Wire 3 saltwater cells in series, and you get 3.3 volts. 6 cells produce 6.6 volts. 12 cells produce 13.2 volts, which is almost exactly the voltage of a car battery. Here is the $3 build. Go to a hardware store, buy a package of zinc-plated washers, which costs about $1 for a pack of 20. Buy a short length of bare copper wire, about $1 for 5 feet. Buy a box of table salt from any grocery store, $50. Cut the copper wire into 2-inch strips. You now have 20 zinc electrodes and 20 copper electrodes. For the electrolyte, dissolve 3 tablespoons of salt in 1 quart of warm water. Dip strips of cardboard, paper towel, or cloth in the salt water. Stack a zinc washer, a wet separator, and a copper wire piece. Repeat. Each stack is one cell producing approximately 0.9 to 1.1 volts. Wire 6 cells in series. You now have a 6-volt battery made from hardware store scraps and kitchen salt. This battery will power an LED light for days. It will run a small radio. It will charge a phone through a USB boost converter. The current output is low, typically 10 to 50 milliamps per cell depending on electrode size, but it is continuous and requires zero external energy to maintain. When the zinc electrodes eventually corrode away, you replace them with fresh zinc washers. Cost of replacement: pennies. Now here is where it gets interesting. The standard zinc-copper saltwater cell has a limited lifespan because the zinc gradually dissolves as it reacts. A typical zinc washer lasts 2 to 4 weeks of continuous use. But there is a variant that extends this dramatically. Magnesium-copper cells use magnesium instead of zinc as the anode. Magnesium has an electrochemical potential of negative 2.37 volts, giving the cell a theoretical voltage of 2.71 volts, more than double the zinc-copper cell. Magnesium ribbon or magnesium fire starter rods are available at camping supply stores for $2 to $5. A single magnesium rod and a copper pipe in a jar of salt water produce 2 to 2.5 volts at 100 to 200 milliamps. That is serious power from a jar. But the most extraordinary variant uses aluminum and activated charcoal. This is the aluminum air battery, and it is one of the highest energy density battery chemistries known to science. Aluminum has an energy density of 8.1 kilowatt-hours per kilogram. For comparison, a lithium-ion battery has an energy density of 0.25 kilowatt-hours per kilogram. Aluminum stores 32 times more energy per unit weight than lithium-ion. The reason you don't have an aluminum-air phone battery is not physics. It is economics. Aluminum-air batteries are not easily rechargeable. You replace the aluminum electrode when it is consumed. This means no recurring revenue from charging cables, charging stations, or battery replacement programs. A disposable battery that lasts 6 months and costs $1 to refuel is a business model nightmare for the battery industry. For a home energy storage application, the aluminum-air chemistry is compelling. Take an aluminum can, cut it into strips for electrodes. Use activated charcoal from an aquarium supply store as the air cathode, about $3 for a large bag. The charcoal provides the carbon surface, where oxygen from the air combines with water and electrons from the circuit. Soak the charcoal in salt water, press it against the aluminum with a separator between them, and the cell produces approximately 1.2 to 1, 4 volts at 200 to 500 milliamps. 4 cells in series produce 5 volts at 200 milliamps. That charges a phone. The aluminum electrode lasts 3 to 6 months of intermittent use. Replacement cost, 1 aluminum can, which is free. The large-scale implications are staggering. An aluminum air battery pack using 10 pounds of scrap aluminum and activated charcoal can store approximately 36 kilowatt-hours of energy. That is more than a Tesla Powerwall, which costs $11,500, stores 13.5 kilowatt-hours, and lasts 10 years. The aluminum air equivalent costs about $20, in materials and stores nearly 3 times the energy. When the aluminum is consumed, you recycle the aluminum oxide byproduct and refill with fresh aluminum. The charcoal cathode lasts indefinitely. Several countries have recognized the disruptive potential of saltwater and aluminum air batteries. In 2019, India announced a program to develop aluminum air batteries for electric vehicles. The prototype achieved a range of 1,000 kilometers on a single aluminum refuel, compared to 400 kilometers for lithium-ion. The aluminum costs $3 per kilogram. The vehicle's fuel cost would be approximately $5 per $1,000 kilometers. That is cheaper than gasoline, cheaper than grid electricity, and the only waste product is aluminum oxide, which is recyclable. The oil industry took notice. Within months, lobbying efforts in multiple countries resulted in regulatory barriers to aluminum air vehicle certification. For home energy independence, a saltwater battery bank provides reliable backup power at negligible cost. Here is a practical system. Build 12 magnesium-copper cells in series using magnesium rods from camping supplies and copper pipe from a plumbing store. Total voltage, approximately 28 volts. Feed this through a voltage regulator to produce stable 12 volts. Connect to a 12-volt deep-cycle lead-acid battery from a junkyard as a buffer. The saltwater cells continuously trickle charge the lead-acid battery, which provides stable power output. Total system cost, approximately $25. This system produces approximately 5 to 10 watts continuously, enough to power LED lighting, charge devices, and run a small radio indefinitely. The chemistry of saltwater batteries is inherently safe. No lithium fires, no toxic electrolytes, no rare earth metals, no conflict minerals. Saltwater is literally the most abundant electrolyte on Earth. The oceans contain 35 grams of salt per liter, which is actually a near-optimal concentration for battery electrolyte use. Every coastal community on Earth is sitting next to an infinite supply of free battery electrolyte. The maintenance cycle is simple. Every 2 to 4 weeks, replace the zinc or magnesium electrodes. If using aluminum air cells, replace the aluminum every 3 to 6 months. Refill the salt water as it evaporates. That is the entire maintenance program. Compare that to a lithium-ion battery system which degrades 2 to 3% per year, cannot be field repaired, contains toxic materials, and costs hundreds or thousands of dollars to replace after 5 to 10 years. The historical pattern is clear. Volta invented the battery in 1800. The basic chemistry has not changed in 225 years. What has changed is the packaging, the marketing, and the price. A AA alkaline battery contains zinc and manganese dioxide in a carefully optimized package. It costs $0.50 and produces 1.5 volts at 2,000 milliamp hours. A homemade zinc-copper saltwater cell produces the same voltage at lower current, but costs 0.05 in materials. The 10x price premium pays for the convenience of packaging. And the $50 billion battery industry exists because most people believe that making a battery requires a factory. It does not. It requires two metals, salt, water, and 10 minutes. The physics is 225 years old. The materials cost $3. And the power company cannot meter a jar of salt water on your windowsill. What two metals do you have in your home right now that could produce electricity by morning?